Hi class, it's me, Mr. Morris again, and we are going to do a review of stoichiometry. Stoichiometry is a method of doing conversions between different types of substances that are involved in a chemical reaction. So we're always going to have a chemical equation involved if we have a stoichiometry problem. So let's look at our steps on how we solve a stoichiometry problem. This should be review for you since we did this early in the spring last year. Using given information, so step one, we're going to use the given information. That's going to be a number of some sort, and some units are given. Using the given information, we're going to calculate the moles of the substance involved in the reaction. So the goal of step one is to get to moles of the substance. Sometimes it's given to you in moles, and if that's the case, you're already done with step one. Step two, write a balanced chemical equation of the reaction. Reaction may be given to you. If that's the case, you're already done with step two. If not, you always make sure that you've got a balanced chemical equation. You can write the equation sometimes, and other times it's given to you. You just need to make sure it's balanced. Step three, use the calculated given moles. So we're going to use the moles we found up here in step one and the balanced equation from step two to stoichiometrically calculate the moles of the asked substance, whatever we're looking for. So our goal in step three is to find the moles of whatever substance it is that we're looking for. That may be the end of the problem. Step three is either the second to last step in the problem or the last step in the problem with your typical stoichiometry problems. It's to find the moles of whatever substance is asked for in the problem. Then step four is to use the moles of what's asked for, so what we just found, the moles of what's asked for, calculated in step three, to answer the question. So it may be that the question asks you for moles. If so, you're done. You don't even have to do step four. But if it's asking for grams or liters or something other than moles, we have an extra step. That's what step four is there for. Okay. So the basic stoichiometry problems, there's three things I want you to think about. Make sure the chemical equation is balanced. We mentioned it in our steps, but always make sure it's balanced. The second thing, remember the top numbers in your ratios and your proportions are the moles of what's given or asked for in the problem. So it comes from the problem. The numbers on top come from the problem. The bottom numbers, so in the denominator of our fractions, those come from the coefficients of the balanced equation. We're going to go through some examples of this in just a minute. I want to finish this section and then we're going to break and do an example problem. Relationships that you have to use to convert your given information into moles can take several different forms. So there's several things that we can do to find moles. So if you're given a number of particles, if we're dealing with a number of particles, the relationship we're going to use is 6.02 times 10 to the 23rd power. It's called Avogadro's number. It's the number of particles in 1 mole. 6.02 times 10 to the 23rd power particles equals 1 mole. Remember, particles can be several different things. Some things we talked about. They can be atoms, molecules. If it's an ionic compound, they could be formula units. They could be ions. They could even be subatomic particles like protons, neutrons, electrons if a question asks for it. It can be any particle, any small piece that you could count. So we're going to say etc. There's more things, but those are the most common ones. When mass is involved, so that's particles is Avogadro's number. When mass is involved, we're going to use molar mass. molar mass. Specifically, molar mass is in grams. It's the number of grams in 1 mole. That's the relationship we use when we're involving mass. And when a solution with molarity is involved, we're going to use this equation. Molarity equals N over V. And to be specific, that's molarity equals moles solute over liters solution. All right, and then if there's a gas involved, we're going to use the ideal gas law, PV equals NRT, to try to find how many moles that we have. All right, so at this point, I want to go ahead and break from the first page of notes. So we've done this first little bit. I'm not going to talk about limiting reactant yet because I want to do some example problems before we delve into that. So let's go to the second page of your notes, and we're going to start with example number 1. Okay, so we have these steps. 1, 2, 3, 4. First step is use the given information to calculate the moles of the substance. That's always going to be step 1. So part A actually asks us to write a balanced equation, so I'll answer that first. For what's written up here, it says solid sulfur reacts with oxygen gas to produce sulfur trioxide. So I can say S8 reacts with oxygen gas. Oxygen's diatomic, don't forget that, it's O2, to yield sulfur trioxide, which is SO3. Now I need to balance it, so I see that I've got 8 sulfurs. I'm going to put an 8 over here and see what that does. 8 times 3 is 24, so I need to multiply oxygen, O2, by something to get 24. I'm going to put 12 to get me to 24. All right, so there's our balanced equation, which, by the way, if you look back at page 1, write a balanced equation of the reaction. Well, that's step 2, so we could go ahead and label that step 2, and we know that we've got step 2 taken care of. Move on to the question. What does it ask us to do? How many grams of sulfur must be burned to give 100 grams, okay, this is my given, 100 grams of sulfur trioxide? All right, so that's going to be our step 1, is always to turn what's given into moles. So once we find out what our given is, we can dive right into step 1. We want to convert it to moles. Right now, I have grams. So how do I convert to moles? This is step 1. I'm going to use my molar mass, 100.0 grams of SO3. And I need to have grams of SO3 on the bottom. I'm going to put 1 mole of SO3 on the top. All right. And if you were to find the molar mass of SO3, that's 3 oxygens times 16, and then sulfur has a mass of, I don't remember, I think it's 32. I calculated the molar mass here. It comes out to 80.06. Okay. I'm going to do 100 times 1 over 80.06, and when you do that, you're going to come out with about 1.249 moles of SO2. All right, that was step 1. Step 1 is find the number of moles of the substance. Then step 2, write the balanced equation. We already have a balanced equation. Step 3, I'm going to use the calculated given moles from step 1, so what I just found, moles, in the balanced equation to stoichiometrically calculate the moles asked for. And remember, top numbers are from the problem, bottom numbers are from the equation. So let's look at it. And I'm going to do step 2. I have that many moles, 1.249 moles of SO3 over, okay, the bottom number comes from the equation, so I've got to look for SO3 in my equation. It's right here, 8 moles of SO3. So that's the relationship between the moles that are given and the moles that are required by the equation to get one batch of the reaction. And I'm looking for what? I'm looking for sulfur. How many grams of sulfur must be burned? Sulfur is S8. So X, and remember your equation, it's written in moles, so it's going to be X moles of S8. And by the way, that's what we're looking for in step 3. I wrote 2, I'm sorry, this is step 3. In step 3, we're looking for the moles of what's asked for in the substance. So I have X moles of S8, and then we got to put the coefficient on the bottom. The coefficient is 1 mole of S8, and that's pretty easy to solve for, just this number divided by 8. So X equals, and when I did that in a calculator, I got 0.1561 moles of S8. Okay, so that's step 3. What was step 4? Step 4 just says basically answer the problem. So step 4 is telling us we need to use the moles from step 3 to answer the question. Well, my question asks me not for moles of S8, but it asks me for grams of S8. So I need to convert it. We're going to do one more unit conversion in step 4. I have 0.1561 moles of S8. I'm going to use my molar mass. Put moles on the bottom, 1 mole of S8 so that I can cancel the units. And then on top, I'm going to put my molar mass for S8, which is 256.48 grams of S8. Punch that in a calculator, you can get 40.04 grams of S8. That's part A and part B of the problem. All right, now if we go down to the next part, part C, it's asking for something different, but it's still talking about the same problem. So we're going to use the same chemical equation. Part C, it gives us, well, it says how many liters of oxygen at STP will be required to produce 5.87 moles of sulfur trioxide. Okay, so sulfur trioxide is my given, and I have 5.87 moles. I'm looking for, so the brown part, or step 3, I'm looking for oxygen, liters of oxygen at STP. That seems kind of important. We'll come back to that. And I'm looking for the units to be liters of oxygen at STP. Let's get started with step 1. Step 1 is turn your given into moles. Well, I already have moles, so step 1 is already given to me. Step 2 is balance the equation. I already have a balanced equation at the top. Step 3 is to do our stoichiometry. So let's do that real quick. Do a calculation to find what I'm looking for. So my given is 5.87 moles of SO3. Coefficient of SO3 is 8. So 8 moles of SO3 equals, okay, I'm looking for oxygen, so I'm going to put X moles of oxygen. Then we got to find oxygen. Got it here, 12 moles of O2. All right, and then I'm going to rearrange. 8x equals 5.87 over times 12, or we could just say I want to move that 12 over here and have x on the top. So it's going to be 5.87 times 12 divided by 8. X equals 5.87 times 12 over 8. Put that in a calculator, you're going to get 8.81. Think, yeah, 8.81 moles of O2. All right, so that was step 3. Step 4, we just need to find what I'm looking for. I'm looking for liters of oxygen. All right, so in step 4, I'm going to find liters of oxygen at STP. Now, if you remember, this is a gas law problem. I've got liters of a gas at STP. Remember that STP is 273 Kelvin, and the pressure is 1.00 atm. So now I could just plug that into PV equals nRT. And we could solve for whatever I'm looking for. I know my pressure, 1.00 atm, that's pressure. And then volume is unknown, that's what I'm looking for, equals, and then N, I just found N, it's 8.81. R is 0.0821 or 206 to be a little more exact. And then T is 273 Kelvin. Now make sure that you always have the right units. If we're dealing with this number, 0.08206, we've got to be in liters, atmospheres, Kelvin, and moles. So I have moles, I have atmospheres, okay, Kelvin. I'm going to find liters, and that's what I want is liters, okay? So if I divide by 1, it's just all these numbers multiplied by each other. So V, 1 times V is V. V equals all those numbers multiplied by each other, which if you do that in a calculator, you're going to get 197 liters. Don't forget to write your units and round to the correct number of sig figs. And that's it for that problem. So let's go to part D. How many grams of oxygen gas are needed to react with 5.50 times 10 to the 20th molecules of S8? S8. All right, so we are given this number of molecules of S8. I am looking for oxygen gas, specifically grams of oxygen gas. So my first step is always to turn this into moles. I've got molecules right now, got to turn it into moles. Molecules are a form of particle, so I'm going to use Avogadro's number, 5.50 times 10 to the 20th molecules. You can write MOLEC for short. We're going to convert that to moles by dividing by 6.02 times 10 to the 23rd power. Molecules, 1 mole of S8. Don't forget to somewhere label what it is that we're dealing with. It's probably a good idea to put it everywhere, but if you didn't, you want to make sure that you at least have it labeled somewhere. Crunch those numbers in a calculator. This times 1 over 6.02 times 10 to the 23rd. Make sure you're using the E button, and you should get 0.000914 moles of S8. Then we have a balanced equation up here. Step 3, we're going to set up a proportion with our given. And again, S8 has a coefficient of 1, so 1 mole of S8, and then equals, we're looking for oxygen gas, so it's going to be X over 12. Okay, X equals 0.000914 times 12. So X comes out to be, when you multiply those, 0.0110 moles of O2. Always check what X is to find out what you're looking for. And then we want to convert. So step 4, try to find what we're looking for, which is grams of oxygen gas. So if I know my moles of oxygen gas, all I got to do is use my molar mass. So I'm going to put 1 mole on the bottom. And then on top I need my molar mass, which is 32 grams of O2 in 1 mole. And when you multiply that, you should get 0.352 grams of O2. That's part D. And then we have part E. How many liters of oxygen? So we're looking for liters of oxygen are needed to produce 25.0 grams of sulfur trioxide at, okay, now which of these is the gas, do you think? And we may not know the state of matter here, but we know the product we're getting is oxygen. So really this liters is related to these over here. Okay, I'm looking for how much oxygen I can get or I need for this reaction. And once I find the number of moles, I'm going to convert it to liters by using temperature and pressure, using the ideal gas law. So we start out with 1. Step 1, convert 25.0 grams of SO3 to moles. So we got 80.06 grams of SO3 in 1 mole of SO3. Okay, punch that in your calculator. You're going to get 0.312 moles of SO3. That's step 1. I've got moles now. Now I can plug it into an equation. Don't forget, step 2, you got to have a balanced equation. We already have that. So in step 3, we're going to set up a ratio or a proportion with 0.312 moles of SO3 on top. And then on the bottom, whatever the coefficient of SO3 is, which in this case is 8. And then I'm looking for oxygen, so I'm going to put X moles of O2. O2 had a coefficient of 12. 12 moles of O2. Cross multiply, so it's going to be 0.312 times 12 over 8. So we end up with X equals 0.468 moles of O2. All right, that's step 3. Step 4, and the final step, is to find out how many liters of oxygen we have there. So I have moles of oxygen, and now I also have temperature and pressure. Okay, so we want to make sure that we figure this out. I'm going to label my variables just to get organized. PV RT. Temperature is 456 Kelvin. R is 0.08206 liter atmospheres per mole Kelvin. Don't forget that sometimes is written liter atmospheres inverse moles, inverse Kelvin. It means the same thing. Moles, 0.468. Volume, that's what I'm looking for. I'm looking for a certain number of liters. And then pressure is 2.64 atmospheres. Okay, now let's solve. PV equals nRT, and I'm looking for V. So I have 2.64 V equals 0.468 times 0.08206 times 456. It's kind of tight, but we can do it. We can do that. Okay, so then we have volume equals 0.468 times 0.08206 times 456 divided by 2.64. And then we end up with volume equals, when you crunch your numbers, you're going to get it something like 6.63 liters of O2. All right, that's a look at several different types of basic stoichiometry. When I say basic stoichiometry, I mean something that does not involve any limiting or excess reactant concepts. So you can convert between grams and moles, as we've seen in the first problem. You can convert using PV equals nRT, or the concept of 22.4 liters at STP. If you prefer, you could do that too. We can convert between molecules and moles using Avogadro's number. And again, PV equals nRT down here. We're going to do more example problems, but first we want to finish up talking about limiting reactant, and we can do some limiting reactant problems and also figure out how to solve stoichiometry with solutions and molarity. That's enough for today, so I'm going to call it off there, and you'll have about a half lesson tomorrow wrapping up stoichiometry problems.